Hey everyone, Joe Grand here to demonstrate some new features of the JTAGulator. The JTAGulator is an open source hardware tool to help you identify on-chip debug interfaces and other interesting things about target hardware. My last formal video about this was back in 2014, and the code has changed quite a bit since then. I've added a bunch of new features, refined some of the existing commands, and squashed a few bugs. So come on, let's check it out. For this demonstration, I do have a Raspberry Pi Zero. This is convenient because it has lots of different features that we can show off. With the JTAGulator right now, I do have all of these different pins connected. I don't honestly remember which pins are what, but it doesn't matter because with the JTAGulator, you basically will have your ground connection, which you need anytime you're connecting different pieces of hardware together or different electronic components to serve as that reference. But then you would take your unknown signals from your target and just plug them into whatever channel numbers you want. When we run our scan, it's going to determine what's what for us. I have CoolTerm running on my Mac, and we'll start there. I can choose the serial port, and it's going to show up as like a USB serial device. So we can connect. It's hard to see on here, but the LED is currently orange. That indicates that it's waiting for us to communicate with it over the terminal program. So what we could do from here is just hit any key once we're in our terminal program, and we get our nice ASCII art. And we see welcome to JTAGulator, press H for commands. For those who are using older versions of firmware, you might realize that this menuing system is a little bit different. I've broken it up now into a sub-menuing system. So we have our target interfaces, JTAG, UART, GPIO, and SWD, and I'll step through each of those. And then we have our general commands down at the bottom. General commands, we have setting the target I/O voltage. That's going to be required no matter what. Anytime we want to do any of these commands, if we want to communicate with a target, we have to set that target I/O voltage. We have display version information, so we can hit I. Firmware 1.10. With the Raspberry Pi, we are running at 3.3 volts. So we're going to set our target voltage. Right now it's undefined, so we can just type in 3.3, hit enter. New target I/O voltage set. Let's just run through these menus real quick. If we hop over to the JTAG submenu, we can see our current list of commands here. I did add this new feature J, identify JTAG pinout. I previously only used to have the I and the B commands, and those are identifying JTAG using what I call the ID code scan and what I call the bypass scan. The ID code scan finds 3 of the 4 required pins of JTAG by basically manipulating the JTAG state machine to get it into a state to read an ID code out of it. ID code is a 32-bit identifier that's not required in the JTAG spec, but it is often used. The ID code scan will find 3 of the 4. It's much faster than the bypass scan, but it's incomplete because you only get 3. The bypass scan checks for all 4 pins, and that takes longer because you basically have to shift data in and read data out on every pin permutation to try to find a result. Usually what you would have to do is you'd run the ID code scan. Once you find 3 pins, you would then run the bypass scan, tell it you know those 3 pins, and then have it search for the additional one. So I finally combined those together into the J command, which does exactly that for you. There are going to be situations though where the J command doesn't work. Maybe the ID code scan doesn't work because some target devices might not have an ID code. Because it's not required, a lot of vendors are starting to be sneaky of like, okay, let's remove things that might not be needed because we know that hackers are starting to look at this type of stuff. Bypass scan generally is going to be active regardless of if there's some sort of protection of the JTAG interface or anything like that, in order to stay compliant. Though that's not always true. A lot of companies lose that compliance on purpose to get rid of bypass scan, which would then make it even harder to find the interface. There's another command I've added, R, which is identify RTCK, which is also known as a return clock or adaptive clocking. This is something that we see in certain types of target devices. Usually it's when you have an FPGA that's running different clock speeds for different modules within itself. So you have this crossing time domain problem, but it helps the target and the JTAGulator and the JTAG hardware synchronize itself. Then we have some other test commands. Once we know the interfaces, you can get the device ID, test the bypass mode. You can do some interesting discovery of querying the chip and trying to figure out how long are the instructions of this particular implementation of JTAG, and then can you cycle through those instructions and figure out how long the responses are. And then the OpenOCD interface is another new feature, and that we'll demonstrate also, which lets you now use the JTAGulator once you've identified the pins that you need on your target you can then hop directly into OpenOCD and use the JTAGulator as that interface to OpenOCD, which saves you a lot of trouble. Normally what you have to do, you'd find the pins with the JTAGulator, you would then disconnect the JTAGulator, plug in some more capable JTAG hardware to then continue on with your attack. Let's go to the UART menu. Here there are fewer commands. We have our standard U, which is identifying the UART pinout. UART is an asynchronous data stream, super common for boot logs, console access, getting login prompts, debug information, and that's generally going to be in human readable text. The new command for the UART menu is T, which is identifying the UART pinout, looking for transmit only. Now, if you've had a previous version of this, you're going to say, well, Joe, you've already had the T command. And I did, but I completely overhauled it. What it used to be is you had to enter the time that you wanted to try each particular pin permutation. It was using fixed baud rates to try to listen in to see if it found something. And it was just a very slow process and really clunky. So this new version is continuously looking for any activity that it might see on those lines. If it sees activity, it's going to try to measure the width of that data stream to try to figure out, is it a UART signal and does it correspond or correlate to some known standard baud rate. We have our UART pass-through mode. That's our common one. Once we find the pinout, we can enter the pass-through mode and now communicate directly to the target and receive information directly from the target over the UART interface. In our GPIO menu, we have a few commands here. One is we can just read all the channels, and that's just going to show us ones or zeros. It's going to read all 24 channels and just give us this one-time measurement of the state of those channels. We have C, which is a continuous measurement. That's just printing an ASCII, zeros and ones on the terminal program to show us the state of the signals. It's sort of a very slow, simple logic analyzer. We have W to write data to those channels, but the new feature here is logic analyzer. The logic analyzer emulates what's called an open logic sniffer, and it uses the SIGROC open source logic analyzer toolset. And the JTAGulator will capture all 24 channels. It's decent, but it's not a substitute for proper hardware. Go to SWD. SWD is the ARM serial wire debug. That's the ARM implementation for ARM architectures of JTAG. It's a 2-wire interface instead of a 4-wire interface. In this case, there's only one command that we're searching for, and that's identify the pinout using the ID code scan, and then you can get the device ID as well. Because of the front end circuitry that I've designed here to protect ourselves and protect the target, that doesn't play very well with a lot of targets that are using SWD. So the software side of this works really well, but the physical interface hardware side, sometimes you have conflicts where if you hook up a device with SWD, the voltage levels aren't going to be exactly right and the JTAGulator isn't going to be able to find the correct interface. I am working on some hardware modifications that will be up on the JTAGulator GitHub wiki that talks about some things you could do, remove the input protection circuitry and or the level translators. Let's get into some demos. So let's do our new TXD only scan. So our starting channel is at 0. Our ending channel is, let's look on here, looks like we have a line going to channel 13. So we can type channel 13. By having the starting and ending channels also means you can have multiple targets set up on your JTAGulator and test each one individually without causing conflict between them. So one feature that is that's here that isn't in the normal U command is the fact that we can receive non-standard baud rates. With asynchronous serial data, with UART data, there's generally a set of accepted baud rates. Vendors are becoming wise to that fact that, oh, hackers are looking at the systems, they want to access these interfaces. One trick that they do is use a non-standard baud rate. That's going to be a baud rate that doesn't fall within range of one of the accepted ones. So here we have the option to ignore non-standard baud rates. It defaults to no because we want to see everything. We don't want to limit ourselves right away. Now it's going to say press spacebar to begin. So we'll start. We can see the LED on here is blinking. So this Raspberry Pi is not sending anything to us right now, which I would sort of expect. Generally, if there is activity or if there is a UART interface, it's going to send data on power up. So what we can do is once we hook up our target, we get the command ready, then we power cycle our target. So let's go ahead and try that. I'm going to disconnect the power. I will reconnect the power. And if we're lucky, then we will eventually see, okay, good. We see some results. Yay. And we see a lot of results because this is constantly looking at changes in data. So, every once in a while it says, I see a change on channel 0. In this case, it's going to measure the bit width, and then, which is the baud measured, and then it's going to take that value and use a lookup table to try to match it to the closest standard baud rate. Let me just abort this now that we found that, so we can hit any key to abort. So if we scroll up a little bit, we have a lot of responses that are 115, 200, which is a standard baud rate. Scrolling through this, I would say with pretty good confidence that's what it is. At one time when it saw a signal, it measured 94, 562 bits per second. And here we see that there is no best fit. That might be an indication that, oh, maybe it's a non-standard baud rate. We should check that out. We have another one, 57.6. Now that we know that TX pin, generally what you would do next is try to find the receive pin. So we'll do that with the standard U command. Again, we have channel 0 to 13. This is a new feature here. Are any pins already known? I had used a feature like this on the bypass scan for JTAG, and I added it now to UART, since if you run the TX command first, now you already know one of the pins. So yes, pins are known. TX is at channel 0, so that's already in there. RX we do not know, so we can hit X. That's going to say there's 13 possible remaining permutations. The way the standard UART scan works is it's going to send a custom user text string of whatever you want to the target on different pins at different baud rates, and then look for a response. So we're just going to use our standard text string of a carriage return. This is another new addition, enter delay before checking for target response. Systems don't always respond to a user input or to data input right away. So we don't want to miss that response. I think the best setting for Raspberry Pi is 250 milliseconds, so wait a quarter second before checking. We have this option of ignoring non-printable characters. UART interfaces normally are designed for human interaction, so we're going to see printable characters, but there might be UART interfaces that are using non-printable. But we don't know anything about the target in theory, so we want to leave everything as gathering as much information as we can. So we are not going to ignore non-printable characters. Okay, so here we are going to hit spacebar, and our Raspberry Pi is already booted up. So, oh, that was actually pretty fast. So we see at these different baud rates, transmit at 0, which we already knew, RX, which is receive. At channel 1, it looks like we're getting some data at these different baud rates. Already, that's a really good indication that channel 1 is the correct pin. You might notice, like, hey, wait a second, there's all these weird baud rates, but there's not 115, 200, which is the baud rate that we calculated for the transmit pin. What's going on? This is a great example of sending data to a system and having it misbehave in some way. Running this command at the login prompt of a Raspberry Pi causes the Raspberry Pi console, UART console, to change baud rates. It really doesn't matter as long as we know TX, and then as long as we see a response, now we know we have the correct pins. Some systems are going to be much more user-friendly where it's going to show you the actual data at the correct baud rate. It just happens that the Raspberry Pi is behaving in this way. Now we know both pins. We have TX, we have RX. We can actually go to pass-through mode and see what's going on those lines. So it's already saved the settings from previously. Now our baud rate is going to send the last detected baud rate from our last scan, which in this case was 28,800, but we know with pretty good confidence that it's 115, 200 based on our other results. We will not have local echo because our terminal program does it already. And now we're in UART pass-through mode. This means that we can type stuff on our computer that's going to send over the USB to serial adapter on the JTAGulator through the microcontroller and pass that data directly to the target. And then the target's going to respond back through that same path, and we'll see the response on our terminal program. I'm going to reboot the Raspberry Pi because I know from our RX scan that it's in some weird baud rate and it's not going to respond to anything. So let's power cycle it again. Fingers crossed. Yes. Okay, so this is all UART data that's being sent from the Raspberry Pi to us over those pins that we just detected. And some of this data stream is what was detected during that TX scan. It's seeing these signals come by and say, oh, I'm going to measure that. So we're going to log in here because that's going to let us show the next demonstration. So I'm going to log in as Pi. So now I'm logged in just to our normal shell. Down here we have a program called pwm.py. That's going to use the GPIO pins and send out a pulse width modulated signal on one of those pins. And it's basically going to be a signal of a varying duty cycle, just to have some activity on that line that we can now go and use our new logic analyzer functionality of the JTAGulator to measure. So to get out of the pass-through mode, we can just hit Control X. Now we see UART pass-through complete, and we're back in normal JTAGulator mode. So we're going to hop over to GPIO. We're going to do our logic analyzer mode. This one requires no, answering of any questions beforehand. It just drops you into this mode where it's now emulating the OpenBench logic sniffer. So we see a warning here. This mode persists through JTAGulator resets, power cycles, and firmware updates. It can only be exited manually by the user. The logic analyzer mode and the OpenOCD mode are what I call secondary modes to the JTAGulator. And that's required in order to support different operating systems, in order to support different types of tools. Sometimes if you close a terminal program, depending on your operating system, that's going to assert the DTR line, and DTR is a data terminal ready line. It's a hardware handshaking line that's not used much anymore for UART interfaces, but it's used in our case of the JTAGulator to reset the device and hold the device in reset during programming. So it's a necessary pin for us. If the terminal program resets the JTAGulator and the JTAGulator is not saving the state of the mode that it's in, you're going to enter your mode, but then as soon as you exit this to go to your logic analyzer tool or go to OpenOCD, it's going to revert back to your menuing system. So we have to save state. It stores the flag of the mode inside of some external EEPROM that's on the JTAGulator. When we're in a secondary mode, the LED indicator is solid red. So if you end up using this mode and forgetting to exit that mode before you put the thing away, a week later you might come out, plug your JTAGulator back in, and it's going to be a red light, and it's not going to be responsive to terminal program input. You're going to be like, what's going on? Hit Control X, that's going to bring you back. So now that we're in this mode, it says entering logic analyzer mode, switch to analyzer software, and use OLS driver at 115.2. So what we can do now is disconnect from the terminal program. I'm going to move over to Linux for the next set of demonstrations. The SIGROC logic analyzer software suite has a command line version and a GUI version. The GUI version is known as PulseView. These are definitely the most stable in a Linux environment. If you go to the JTAGulator wiki and click on the Logic Analyzer tab, you'll see a list of known issues with all these different software platforms. I'm just going to run the PulseView tool, and it has this thing. It's going to scan for any available devices. It won't find our device because it doesn't search for SUMP interfaces that way. It searches for other hardware that's using other drivers. So here's our main screen. We can click on the little arrow here to connect to device, go over to OpenBench Logic Sniffer, serial port. Our serial port is going to show up here as USB 0. We can see FT2, FT232, 115, 200. So at this point, we should be able to scan for devices, and it's going to go out and query the serial port, sending the correct commands to see if it gets a response back. So see if that's going to work. Yes. So the JTAGulator responds with, I am the JTAGulator, I have 24 channels. The logic analyzer can also support level triggers. So we can trigger if a signal is a logic level high. We can trigger if a signal is logic level low. Again, a very basic logic analyzer. So now we see a blank screen with no data yet, but we can see our 24 channels. We can set our capture parameters. So we have, how many samples do we want to take? How fast do we want to take them? I think the ideal one for this demo, I'm going to lower it down to 5 kilohertz. So we're going to take slower samples, but that means we'll capture for a longer period of time. And I think if we hover over this, we'll see, okay, so our total sampling time right now is 205 milliseconds, so a fifth of a second. So now we should hit run. And we see on channel 7, here's the little pulse stream. Hit it again, same channel, but the pulse is a little bit wider because that PWM code we're running is varying that duty cycle. So we definitely see activity on that line. What I would probably do at this state if I was really looking at a system is say, okay, I see activity there, so I would then go and turn on my scope and see what's actually there. So if we take a look here at channel 7, we can actually see that there's an active signal and it's moving. The pulse width is getting bigger and it's getting narrower. We were seeing slices of time on the logic analyzer through the JTAGulator, but now we see it's actually a moving signal. What we need to do to exit that logic analyzer mode is connect back up to the JTAGulator. We can use screen. You can use any other terminal program too. USB 0, 115, 200. So now we're back in here. If I hit any keys, we're not going to see anything, but if I hit Control X, that's going to exit out of that mode, and now we're back where we expect. So now we're going to show off the new JTAG J command, and that's going to be that combination of ID code and bypass scan together. We'll do J, channel 0, channel 13. Here's an option of bringing the channels low between each permutation. You usually don't have to do that. Generally, you can leave the settings and say no, but there might be some systems that require some other pin that you're connected to go low before it enables a JTAG interface or whatever it is. So generally what I'll do is a normal scan without bringing any channels low, and if I'm not seeing anything, I will then try again bringing channels low. Okay, so now we're gonna hit spacebar and see what happens. This is gonna try all the different channels, looking for the ID code by basically changing the pin numbers and shifting the JTAG state machine into the certain state to read the ID code out. So are we gonna see, oh, we saw something. Yes, success. We just scanned 24,000 permutations to find the correct pins, the unique pins that we need to communicate to the target device over JTAG. We see TDI, TDO, TCK, and TMS. The JTAG scan also is gonna say, oh, I've detected an interface, let's read the device ID. We also see the T reset pin, that's a test reset pin that's optional for JTAG discovery. That resets the state machine of JTAG back to the beginning, but you can also do that with a software sequence. But the fact that the Raspberry Pi has it, we found it. And the way that it finds it is basically once it detects what it thinks is a correct pin out and it can read the ID code, it just uses those pins and then pulls each subsequent line, each remaining line of the channel range low, to see when it does not receive that device ID anymore. Because if you're holding that pin low, the JTAG state machine is not gonna respond. So here's the RTCK adaptive clocking. What this is basically is systems that support RTCK look for the JTAG clock. It's gonna send an echo of the clock back to us when it's ready for the next thing. So it's a way to synchronize clocks between systems. TCK is already known, yes, because we just detected it. We will not bring channels low. So it really only has to check the 13 other channels. So let's do this. We know TCK is 13, now RTCK is 9. If we looked at TCK and RTCK at the same time on a logic analyzer or on an oscilloscope, RTCK would be the same clock, just slightly delayed. So let's quickly run this OpenOCD example. We can just hit enter for all of the pins that we know. Now it's gonna say entering OpenOCD mode. Now here's an example of the command line string that we need. So I'm not going to go into all sorts of detail about OpenOCD other than to say it's an extremely powerful open source JTAG environment that lets you debug and develop and really hack on and modify and manipulate target devices. So I'm going to exit out of screen. We are going to type in that command. We'll launch OpenOCD with the interface of Bus Pirate. The way that the JTAGulator works for this mode is it emulates what's called the Bus Pirate binary protocol. And the Bus Pirate is an open source general purpose hardware hacking tool. They worked with OpenOCD to create this binary protocol to let the Bus Pirate, which is also a serial based interface like the JTAGulator, work with OpenOCD. So we're going to just put in some additional command line settings, set our port, which is TTY USB 0. And now we need to not only tell the OpenOCD what our interface is, which is our JTAGulator Bus Pirate, we need to tell it about the board or the target that we're hacking on. The Raspberry Pi Zero has a configuration file that exists. It kind of sets up some settings that OpenOCD needs. So if you're working with a target that you don't know, you might have to mess around with these values. So we're just going to drag that in here. And now, if we are lucky, OpenOCD will communicate to the JTAGulator, and then that's going to shift bits in the right way to communicate through the JTAG interface to the Raspberry Pi. And it does. So we see a lot of different messages and stuff. The most important is it says Bus Pirate JTAG interface ready, and then JTAG tap, device found. This ID code matches what we already found, and it even breaks out a little bit more and says, oh, it's a Broadcom chip. Version number. So now we're actually communicating with that device. ARM 1176 has some breakpoints. So we're good to go. We can actually see on the JTAGulator hardware right now, the LED is blinking. So that's kind of blinking as it's receiving data from OpenOCD. So let's just open up a new window. Now we're going to telnet to the interactive command prompt of OpenOCD. And here there's like a whole lot of commands we can look at and stuff. But what I'm going to do is halt the system, So now I can actually stop the Raspberry Pi from operating. Now the chip is halted, and really from within OpenOCD, which also supports GDB, GNU Debugger, you can start debugging a system just like you normally would a piece of software. You can single step through code, you can view registers. So let's take a look at our registers, our current program counter and other stuff. We can jump over instructions, we can do whatever we want. Here we can step. So this is just showing that we can manipulate a system through OpenOCD. What we can also do is dump memory. Probably what's cooler is we can do the dump image command, and we can dump a larger chunk of memory out to an actual binary file. And that's going to let us analyze it offline a little bit easier. So we'll do 1,000 hex bytes of that. That's going to be a little bit slow. I think it takes around 16 seconds. So we've dumped our 4 kilobytes. Let's just quickly take a look here. We'll use XXD. Take a look at dump.bin. So now we see just a tiny section of memory from the Raspberry Pi that we've just pulled out over JTAG. We see a whole bunch of boot parameters and other information here. And so let's just finalize this. We'll exit. We're going to go back to the JTAGulator screen, hit Control X, OpenOCD mode complete, and now we're back and ready to do more stuff if we need to. So there you have it. A currently up-to-date video on the JTAGulator. The tool is fully open source, so you can find all of the information about the hardware design, the firmware, all that stuff on my website if you go to grandideastudio.com and search for JTAGulator. Once again, I'm Joe Grand signing off. Thanks for watching. JTAGulator new feature description video, successful.